All right. So, we are moving into applications of Gaussian elimination. We are just on the verge of where this class gets hard. So, so we're going to talk about today. Yes. So, the traditional breaking point of this class is in chapter 4, which is about vector spaces. So, basically, this chapter is going to be about using row echelon forms to solve systems of equations and interpreting those results. Some of that's going to smell a lot like 241. And then in 2.6, we'll talk about computing inverse matrices. That's just, if you know if you know how to divide by a number, you know what's going to happen with inverse matrices. And then we'll do determinants, which is also pretty easy because it's calculational. And then chapter 4, we launch into the realm of abstract vector spaces. And traditionally, I'm not worried about you guys, but traditionally, in linear algebra, that's where the wheels start coming off for people, because we're going to talk about things like, what if instead of vectors being little arrows in R3, they were functions and I could add them together? Because that acts like vectors too. So that's going to be sort of where we build the idea of what we're going to use this stuff for in the land of differential equations. So this next week will probably seem kind of easy, or at least comparable with what came before. And chapter 4 is a pretty significant lift in the level of abstraction that's happening, but it's also where the real meat of the class is, like the applications that come out of this. So just be looking forward to that. You can read ahead if you want to get ready. So 4.1 will be really easy because that's just a review of stuff from 241 and the end of 143. But 4.2, I think, is where the real sort of new stuff is going to start for almost everybody. But today, we have 2.5. Is applications of row reduction. And specifically, I think in the book they call this Gaussian elimination. So what can we say about a system of equations using the techniques of row reduction? Is kind of what we're after today. We've already hinted at what some of this is going to do. So if I write down as an example from last time, x plus y is equal to 1, and x plus 2y is equal to 3. I could solve this directly, but if I put this into the form of a matrix, an augmented matrix, I have my coefficient section, 1, 1, 1, 2, and my right-hand side section, 1, 3. If you row reduce that, in fact, if you took it to reduced echelon form, or row echelon form, you would get the matrix 1, 1, 1, and then 0, 1, 2. So this would be sufficient if all you cared about was the pivot columns. If all you cared about was where these pivot columns were, and there are cases that we'll talk about today where that is all you care about, you could stop here. You don't need to go all the way. This is called Gaussian. To get to this step is called Gaussian elimination. I'm actually not going to be doing careful row reductions in here because you should really just be practicing those, and watching me do it on the board is really boring. So I'm just going to row reduce stuff. It'll either give you row reduce forms or I'll do it quickly. So this is Gaussian elimination because we've landed on row echelon form. If I go further and I want to put it into reduced row echelon form, so I continue and I get the matrix 1, 0, 1, minus 1 rather, 0, 1, 2. This is called Gauss-Jordan elimination. And a natural question you might have is, why on earth wouldn't you just do that every time? Computers do it. So why do we care about this? And the answer is, putting a matrix into reduced row echelon form is incredibly computationally expensive. And in practice, matrices that show up when you're doing things like approximating fluid flows or data science could be million by million matrices. And if you have millions and millions of extra computations to do, you're just burning electricity and computer time. So this is still in wide use. Notice that the pivots are in the same spot. Those didn't move between row echelon form and reduced row echelon form. So if that is all I cared about, I could have stopped here. If I'm asked to solve the equation instead, this is a particularly easy way to do it because you can just read off 0x's plus 1y is equal to 2. So y is equal to 2. And 1x plus 0y's is equal to negative 1. And so x is equal to minus 1. Reduced row echelon form is extra useful for finding specific solutions, or if you're asked to solve or characterize the solutions. Whereas the row echelon form, if you stopped here, you may have remembered in your past solving systems of equations having to use a method called back substitution. If you stopped here, you would have the equations x plus y is equal to 1 and y is equal to 2. Back substitution. And then the idea would be, well, I've got a y, so I can plug back in to figure out what x is. So x plus 2 is equal to 1, which means x is minus 1. So it's more annoying because there's more steps. So the upshot is, if you're asked to find solutions to an equation, work in reduced row echelon form. Okay. So this is not a very exciting set of equations to use. So let's look at something slightly more complicated here. So let's look at this example. If I wrote down something like 1, 1, 1, and 1, 1, 2. This is an augmented system, or augmented matrix for x plus y is equal to 1, x plus y is equal to 2. Okay. If you row reduce this, you're going to end up with 1, 1, 1, 0, 0, 1. You locate the pivots of this matrix. Remember, pivots just mean the places where the leading ones are. So these are the pivot positions. And if you translate that back into a system of equations, you end up with x plus y is equal to 1 and 0 is equal to 1, which is false. So this is false. And so this system has no solutions. And the other way of saying that is it's inconsistent. But notice, there's another way to characterize this in terms of the pivots themselves. The location of that pivot in the last column told us, without having to do any other interpretation, that this was an inconsistent system. So a lot of what we're going to be doing over the next couple weeks is translating information about pivot positions into structural information about systems of equations or matrices. So let's just observe that if an augmented matrix has a pivot in the last column, in the augmented column, the system is inconsistent. And we can say more than that. If it doesn't have a pivot in the last column, it's consistent. If the system, or if the augmented matrix, if the augmented column does not contain a pivot, the system is consistent. So if I'm doing work to try to figure out a solution for a system of equations, before I go through the trouble of trying to figure out what the solution is, I can just read off Is there even worth continuing with the work, depending on where the location of that pivot is? If there's a leading one in the augmented column, just stop. If there's not, you have solutions to find. So in this particular system of equations, I wouldn't go any further. So let me give you one where you do have to go further. All right, so this is going to be typical of the way my approach to these questions is going to work. So, oh yeah, go ahead.
If you ever end up with a row that's like 0, 0, 1, or like anything that's like all zeros, like for
You can stop immediately.
At any point in the row.
Yes, and if you come across that anywhere, if you end up with a false equation at any step in a row reduction, the whole thing is not solvable.
So this only applies if it's an augmented matrix?
Yeah, so if I'm thinking about an augmented matrix, I'm saying it's not solvable because a general matrix doesn't necessarily represent a system of equations. If I'm thinking about it as representing a system of equations, the system of equations that matrix represents is not solvable. Right? That's kind of what it boils down to. All right, so let me show you a different system here. So let's look at this one. X plus 2y is equal to 6. And 2x plus 4y is equal to 12. And I say, find all solutions. So I could load you up with vocabulary and theorems, but I'm going to show you practically what's going on here. Right? So we're going to try to find all the solutions to this equation. So if I wrote down the augmented matrix that represents this, and you were doing this on an exam, I would just tell you that this row reduces to this form. So this row reduces to 1, 2, 6, 0, 0, 0, unless you were being asked to actually show me that you know how to row reduce. So what exactly is happening here? So I have one pivot. There's going to be an infinite number of solutions. So let me write down exactly what we're saying. What we're saying here is that x plus 2y is equal to 6, and also 0 equals 0, which is always true, right? There's no restrictions on the 0 is equal to 0. So what we're saying is the following. If you told me the value of y, I could tell you the value of x that solved the system. If you told me the value of x, I could tell you the value of y that solves the system. So one of these choices is a free choice and the other one isn't. In order to make this algorithmic and consistent, we are always going to use the same variables as the variables that are not free choices and the ones that are. So a variable that corresponds to a pivot, if I'm thinking about this is the x column and this is the y column, x has a pivot in its column. So I think of that variable as the bound variable. There's no reason to do it this way other than to be algorithmically consistent. X is going to be what we call bound, by which I mean it's determined by the choice of y. If you like, you could think about it as a dependent variable. The y is a free choice and x is not free because the x must force this equation to be true. Y is called a free variable. It's a free choice. You can pick any y you want, and I can tell you the x that goes with it. So the convention that we use in linear algebra is pivots are bound, and columns that do not have a pivot are free. So if I was going to characterize the solution set to that system of equations, which is not a very interesting set of solutions, I would write the following down. The set, okay, so the first thing is, if x is a bound variable, I'm going to solve for it in terms of the free variables. The free variables are independent, the bound variables are dependent. X is equal to 6 minus 2y, and y is an independent variable. Or if you like, you could say a free variable. So I can't tell you what y is, but once you pick it, I can tell you x. If I wanted to write down a description of the complete solution set to that system of equations, I would write, okay, well, it's a whole bunch of points x and y. I'm going to write this in vector form to make it very clear what the connection is between the stuff we did in earlier classes. It's a collection of points x and y. What conditions do they have to meet? Well, I can't tell you anything about y because it's an independent variable. But the x's, once you've chosen the y, must be of the form 6 minus 2y. So that's it. That is a description of the solution set. Any y that you give me, if I plug it in here, that set of points, x and y, will solve those equations. So, for example, if you picked, y is equal to 1, then you would get the equation 6 minus 2, 1, which is 4, 1. If you plug that in up there, you get like 4 plus 2 equals 6. Okay, that's a solution to both equations because they're the same equation. If you, for example, picked y is equal to 3, you would have 6 minus 6 and 3, which is 0, 3. That's a different solution, and every value of y that you choose will give you a different solution to the equations. So there's an infinite number of solutions here. Because there's a free choice, we have infinitely many solutions. And if I want to use all of that vector math we spent all that time learning, if I could pull this apart, I could give you a parametric description of the solution set. So if I took this vector and I took the part of it that is only numbers, and I added it to the part that only has y's inside of it, so hopefully it's clear that what I'm doing here is if I add these back together again, I get this. But I've made a vector that there's a y in every spot, so I could factor out the y if I wanted to. And I get this. 6, 0 plus minus 2, 1 times y. If we were back in 143, what have I just written down? It's a line. That is a parametric equation of a line. What that says is, this, whatever the original configuration of stuff is, the solution set consists of a line. Here's how I get to the line. This is the direction vector, and the y is just choosing how far I travel along that line. The solution set to a system of linear equations is linear. So if I was writing down a complete description of what's happening here, I would say this system of equations is consistent, since it does not have a pivot in the last column. It has infinitely many solutions because there was a free variable, and this is what the solution set looks like. Yep.
In the book, they say like y equals t.
If it makes you more comfortable to inject a parameter like s or t, you can. I think that is it's an artifice that gets used to separate the fact that there's a parameter running around, right? But if you're going to say that the y is a free choice, you can just use y as your choice variable if you prefer. All right, so let me write down a more interesting example of how this works. Because maybe it doesn't surprise you that if I give you a system of equations that's a line and literally the same line, that the solution set to a line and a line that are the same line is the line back again. Right? That not geometrically, not a lot of interesting things happening there. So I'm going to give you two planes this time, and we'll describe the solution set. All right, so I'm going to give you the plane x plus y plus z is equal to 1. There's a plane. And I'm going to give you another one. So let's say x minus y plus 2z is equal to 4. What should you expect the solution of this, the intersection of these two planes to be? It's good to actually have intuition for the geometry of what's happening. So I have a plane. And then I have a plane. And then I have another plane that's sort of sitting in space that's not parallel to it. What sort of solution set do you think that should have? It should be a line of intersection, right? There's a line that dictates where those two planes come together. It's like the sidewall and the front wall come together in the line that runs up and down the corner, right? So we should expect that when I solve this system of equations for its solution set, I should get a line out the other side. There should be a line of solutions to characterize. Well, let's actually do it and see. Okay, so we write down our augmented matrix, 1, 1, 1, 1, 1, minus 1, 2, 4, and then I row reduce it. And I'm going to make a bunch of qualitative assertions after my first step of row reduction. 1, 1, 1, 1, 0, minus 2, 1, 3. Ugh, -2, that sucks, oh well. I guess I could fix it so it was nicer, but this is the way they work. Okay, so already right now, I can tell you if this is consistent or inconsistent and how many solutions there are. I can't tell you what the solution set actually is, but I can tell you all the rest of it. There's a pivot here, and even though it's not a 1 yet, there's going to be a pivot there as well. All right, first question is the system consistent? Yeah, there's no pivot, and the pivots are here and here. There's no pivot in the last column. This is definitely consistent. There is an answer. So it's consistent. Which of the variables are bound and which ones are free?
X and Y are bound, Z is free.
X and Y are bound variables. Z is a free variable. Z is free because if this is the X, Y, and Z column, Z does not have a pivot, which means that's going to be my free choice. Okay. And this is going to be annoying. So I'll do one more row reduction step here. That's going to get me to reduced row echelon form. That's the information I can get out of this form, but if I actually want to write the solutions down, I should go all the way down to RREF, to Gauss-Jordan form. So 0, minus 2, 1, 3, and then, gosh darn it, okay, let's see, 2, 0, 3, 5. I did 2 times the first row plus the second one and then replaced the first row. You're allowed to do that. I'm avoiding fractions.
So you don't have ones.
Well, I could put them there, right? 1, 0, 3 halves, 5 halves. 0, 1, minus 1 half, minus 3 halves. That'll do it. Well, because I just like, I don't know. Come on, man. Okay, so the nice thing about working with, oh, I was making fun of myself for saying okay, so there you go, there was an okay, so. The nice thing about this form is I don't have any extra work to do with substitutions. I don't really ever want to do back substitution when I'm solving these, especially if there's a free variable involved. So I'm going to look at this. I'm going to write down a characterization of the solution set based on that matrix. So I have X is equal to 5 halves minus 3 halves of a Z. That's what the first equation tells me. So the first equation here is actually X plus 3 halves of a Z is equal to 5 halves. But X is a bound variable, so I solve for it. I have Y minus 1 half of a Z is equal to minus 3 halves. Y is a bound variable, so I solve for it, and that gets me Y is equal to minus 3 halves plus 1 half of a Z. And then Z was free. Free choice. So that is the most basic description of the solution set you can come up with. I told you what the free variable is and how to find the other two in terms of it. But geometrically, and with the stuff that we're driving to abstractly, I actually probably want to write this in parametric form. So X, Y, Z is equal to 5 halves minus 3 halves Z minus 3 halves plus 1 half Z, Z. And if I really want to pull it apart so I can see exactly what the structure is, I'm going to write this as 5 halves minus 3 halves, 0, plus minus 3 halves, 1 half, 1, Z. If you really hate fractions, you could multiply all that by 2 if you really wanted to. Yep.
Is it
I did something wrong.
minus 1 half Z?
Where did I blow it?
Wait. No, it's not.
No, I think it's right, because this was minus over here, so I pull it over to the other side. Next thing when you're solving one of these questions, the very next thing you should do is say, does my answer make sense? Does it comport with what I thought was going to happen? Generically, I've got two planes sitting in R3. Their intersection can't be a point. I can't have two planes come together in a single point. The only thing that could happen is they are aligned or they're parallel to each other. That's all that can happen. So to me, this seems like a reasonable answer. And it's definitely aligned. And so I'm going to do one more of these, and then we're going to start talking about some more interesting consequences of what we're doing here. So I'm just going to start with a matrix this time. Do one more calculation. Just to show you what happens if there's more free variables. It's not all that surprising. Okay, so let's suppose that you had a system, so another example, that looked like this. 1, 1, 0, 1, 2, 0, 0, 1, 1, 3, 0, 0, 0, 0, 0. Okay, now this is a harder question to interpret geometrically. I've got two hypersurfaces, hyperplanes in R4. Those can intersect in a whole lot of weird ways that you're not used to because you can't visualize in 4 dimensions. I can't either. First step, is this a consistent system?
Yes.
Yep. What are the free variables? What are the bound variables? Okay, let me give you some conventions here. When you go above 3 variables, this is the sort of where most people flip over to talk about x1, x2, x3, and x4 as the variables. But if you like alphabets that don't come in order, another convention is to call this x, y, z, and then you go back to w. I don't know why they do that, but like that's the other sort of standard set of coordinates in R4. It's not a 4, that's a 1. Okay, so same process. If you're getting the idea this is mechanical, it's because it is. Mastering these mechanics is going to make everything we're doing later easier. 2 pivots. So x and z are bound, and y and w are free. It's a consistent system. There are free variables. So there's an infinite number of solutions. If I translate these into equations, I get x plus y plus w is equal to 2, and z plus w is equal to 3. My bound variables were x and z, so I write x is equal to 2 minus z minus w, and then what's the other bound variable? Z. Z is equal to 3 minus w. If I write the solution set out in this case, x, y, z, w is, okay, x was bound. Y is free. Wait, where's the y?
Yeah.
Hold on. What's this z doing here? Sorry about that. I think I fixed it. Is that right? Yeah. Okay. Z is bound. W is free. Notice every single time we do this, the entire solution set is entirely in terms of the free variables. The bound variables vanish because they are derived from the free variables. So if you're going to finish pulling this apart, 2, 0, 3, 0, that's your sort of location vector, plus the vector minus y, y, 0, 0. There's your y vector. Plus the vector minus w, 0, minus w, w. The idea is if I took these 3 vectors and put them back together again, I'd get this. But I've got a numerical vector, a vector that a y could be factored out of, and a vector that a w could be factored out of. And so the result is the numerical vector 2, 0, 3, 0 that's always there, the vector -1, 1, 0, 0 times the parameter y, plus the vector -1, 0, -1, 1 times the parameter w. What is the solution set this time? Geometrically, what is that? It's linear. No, it's a plane. So it doesn't. You might not recognize this as a plane, but look, it's a location vector to tell you where to go, and then two different vectors pointing two different directions that tell you how the plane is oriented in space. Every solution to that set of equations that we wrote down sits on this two-dimensional plane sitting in R4. Why is it two-dimensional? Where does the idea of dimension even come in here? The number of parameters that we see here tells us how many dimensional the solution set is. So the number of free variables is a measurement of how much freedom you have in the system. One way of thinking about linear algebra and the power of linear algebra is it took this potentially infinite collection of solutions but reduced it to a pretty basic combination of really simple things. This collection of infinite combinations of x, y, and z really boiled down to like a fixed vector plus scalar multiples of two other fixed vectors. We've taken this infinitely sized thing and replaced it with three pieces of information. This is part of the reason why linear algebra is used. You can't imagine what it looks like. So I will say in practice, the sort of things that you do when you're working with these things in large systems, the system itself might have solutions that have 25 parameters or 30 parameters or 62 parameters, or you're in machine learning and you've got 1 million parameters. Yep.
So if we're working with the linear equations and we get two parameters, it's always a plane.
You think of it as, I think of it as a plane, right? You can think of it as a, I mean, really is a two-dimensional linear subspace of R4. Or plane.
That's a plane.
Yeah, that to me that's a plane, right? So a three-dimensional linear subspace of R4, I don't have a good name for it, right? It's like a hyperplane of some kind. All right, so I have one last thing to point out here that's going to turn out to be really important, and then I'm going to talk about some matrix multiplications. Not another example, just like let's look at this. So if I don't think of coefficient matrices, or of augmented matrices, but instead I think of a coefficient matrix. So I want you to think about, let's think about for a second, AX is equal to B. And what I mean by this is I have a matrix A times a vector x1 down to xn is equal to a fixed set of numbers b1 through bn. If I wanted to write that down as an augmented matrix, it would look like this. A augmented with B. That would be the augmented matrix. Okay. So I want to think about the case where that vector on the other side is just the zero vector. So I want to think A times x1 down to xn is equal to zeros down here. Oh, I got to be careful here. Let's be a little bit careful. If A was m by n, and this is n by 1, how many entries should be in this column? Not n, m. Remember, when you matrix multiply, m by 1, the outside numbers tell you what you expected dimension of the output should be. So this is called a homogeneous system. So it may not be surprising to know that a homogeneous system always has a solution. I don't have to worry about those being consistent because I know what is always going to solve a homogeneous system. The zero vector. If I put 0 in right here, anything times 0 is equal to 0. Or if you think about the system of equations, if I just stick a bunch of zeros into it and there's zeros on the right-hand side, 0 is going to be equal to 0. So a homogeneous system AX is equal to 0 is always consistent. Because x is equal to 0 is always a solution. Always. However, sometimes it's unique. So we have a condition we can use to check that. If every column of A is a pivot column, then AX is equal to 0 has only the solution X is equal to 0. Based on what we've just done here, that shouldn't be that surprising. What that's saying is there's no free variables. So if I write down AX is equal to 0, and there's no free variables, but you know that means there's a unique solution, right? But you already know 0 is the solution, so there can't be any others. If every column of A is a pivot column, the only solution to X is equal to 0 is the trivial solution, X is equal to 0. And these matrices are so special. There's a whole chapter dedicated to them, which is 2.6. These are going to turn out to be the matrices that have inverses, like multiplicative inverses. And this is kind of where some of the abstraction is going to start picking up. These are the matrices on which algebra works. So let me point some things out here. So if I wrote down the matrix 1, okay, so what I want to be true, this is what I want. I want this to be true. If I was in the land of algebra, and I tell you that A times B is equal to 0, what can you conclude? The numbers here. Yeah, I mean, either A is equal to 0 or B is equal to 0. Use this all the time. X minus 2 times X plus 1 is equal to 0. So X is equal to 2 or X is equal to negative 1. You do that crap constantly. Factor things and say one of them is equal to 0. What if I did this? Is that the 0 matrix? That's the 0 matrix? What's the product of those two matrices? Let's see. 1, 0 dotted with 0, 0 is... Oh, wait. I gotta do this. Okay, I fixed it. 1, 0 dotted with 0, 0 is 0. 1, 0 dotted with 0, 1 is 0. 0, 0 dotted with 0, 0 is 0. 0, 0 dotted with 0, 1 is... Oh, poop. The basic thing that we do all of our algebra with is false. If A times B is equal to 0, so what? You can say nothing. That's terrible. So now I'm going to point out another complication. I want you guys to tell me what the problem with this one is. So I'm going to use that same example. What if I took 1, 0, 0, 0, and I multiplied it by, oh, I don't know, how about 0, 0, 1, 1? What's that equal to? Oh, it's a 0 again. Okay. What's the issue with what we just wrote right here? In fact, I'm going to tell you what I really would like to be true. Here's one of the things that's so deep in your brain you don't even question it. If A times C is equal to B times C, then A is equal to B, right? If A times B is equal to A times C, they're definitely equal to each other because they're both equal to 0, right? A times B is definitely equal to A times C because they were both equal to the 0 matrix. Can I cancel the A?
Yes.
What if you did? What'd you get?
0, 0, 0, 1 equals 0, 0.
Which is false. Right? So,
How do you know that's false?
well, if you make two things that aren't equal to each other, the entire number system collapses into two objects, the 0 matrix and the multiplicative identity. It's not a very interesting number system. So the issue here is actually the fact that these matrices are going to turn out to be matrices that, you notice, they don't have pivots in every column. I've set them up so they don't have pivots in one of their columns. These are going to be matrices that don't have multiplicative inverses. So if a matrix doesn't have a multiplicative inverse, I can't do algebra with it. I can't divide by it. That doesn't make any sense to divide a matrix, but I can't do that, right? So these matrices that don't have enough pivots, square matrices are extra special because if I start with a square matrix and I multiply it by another one, I get a matrix of the exact same size out the other side. And algebraically, everything seems symbolically like it works until you start wanting to cancel things. And then the zero property fails. And like this sort of the multiplicative rule of equality, which you may have even learned by that name if you were in a fancy algebra class in your first go, that also fails. So you can take an equation and multiply things on both sides and the equation will still be true, but you're not allowed to take it back away again. If I give you an equation that has an a on both sides, you can't cancel it. So just to illustrate the point more thoroughly, if I wrote down something like AB is equal to AC, and you are trying to do algebra the way you did it in the past, you might say, oh, that's the same as AB minus AC is equal to 0. And I'm going to factor out the A to get A times B minus C is equal to 0. Be careful to factor out on the left because matrix multiplication order matters. And then what can you conclude? Nothing. You can conclude nothing. You have a product of matrices that's equal to 0, but that doesn't tell you that either one of the matrices was 0. So I want to be able to use matrices to do algebra. I want to do this. I want to be able to say, if I was looking at AX is equal to B, it sure would be nice if I was working in number land and I could just divide both sides by 2 to get x is equal to 2. That's what I would like to be true here. Or more precisely, since I told you guys division doesn't exist, 2 inverse times 2x is equal to 2 inverse times 4, and so x is equal to 2. I can't do that here. I can't divide by a. I can't even multiply by the inverse of a unless I know it exists. So this is what we're going to talk about next time. When can I say that this is true? When does the 0 property hold? Yep.
Is it the determinant equals 0?
And the determinant is what we'll do in 3.4. And so if you guys wondered what the determinant was really for in earlier classes, the determinant tells you if a square matrix has an inverse or not. The good matrices are the matrices where the determinant is not 0. The ones that are hard to work with are the matrices where they are. And if you look at these, both of these have determinant 0. So it's kind of all those ideas are going to kind of come together when we study which matrices have inverses and how we find them. And that's really like a lot of the use of linear algebra boils down to exactly that idea. In fact, if we go back to 241, do you remember the second derivative test from 241? What the second derivative test from 241 was actually asking is if the Hessian matrix was invertible. But I couldn't tell you that in 241. I had to tell you that's what you're doing. What you're saying is the derivative locally keeping all of the information, or is it throwing stuff away? If the derivative is invertible, it means if you feed in a little plane comes out. If the derivative is not invertible, it means a plane might turn into a line, which means you've crushed information out of the problem. So, yeah, this is like, to see this all as glory, you've got to take like a 4th year like upper division math class to really figure what's going on here. But essentially, all of this links up with derivatives. That's kind of what we're going to do with it when we go further. All right, I'll see you guys next time.